Okay, last time we were talking about the call stack, right? This is about where we left it. The call stack, at the end of the day, it is just a stack, actually. And it's the part of memory where we keep track of the information of the current method being run. Really, that's actually the thing at the top of the stack. There's additional stuff on the stack, which is the information related to the method that was currently running, never finished, but requires this method at the top to finish before it can carry on. That's the idea. And I'll show you a visualization of this in a moment. It's called a stack. You push and pop stuff from the top of the stack. You have a main method that's on the stack that calls another method, that calls another method. That method finishes. This method continues and finishes. This method continues and finishes. Like, that's the idea. It's a stack, it grows and shrinks. And you, as humans, kind of operate on a stack throughout your everyday life, right? Like, and you've probably been doing this when debugging a problem. Like, how many times have you had this problem? Like, you're debugging problem A, but when working on problem A, you realize there's an issue B that you need to solve. So you're like, well, okay, I got to fix B. And then you're working on issue B, and then on that you discover C needs to be fixed. So then you fix C, which means then you can fix B, which means then you can fix A, right? Like, this type of thing, like, you do a lot in an everyday thing. Like, your attention usually follows that. Like, I'm doing this, someone comes and knocks on the door, someone, you pick up a phone call, okay, you're done, you talk to, okay, then you're back to work. Like, this is how you usually kind of operate, right? Obviously, there's a lot of exceptions, but this idea happens a lot. A call frame, these are the things that you create that we put on the call stack. A call frame is just a fancy way to say, like, it's the grouping of information we need. It contains all of the relevant information we need for the method being run. This contains things like the method parameters, like what variables got passed to the method. It contains things like the local variables that the method also has. This could include primitive types where the value is stored in the call frame, where it's like I have an integer a that equals 5, okay, it's stored there. But it could also be things to references to objects where you have a variable, my stack, which is a stack reference variable, but it's containing a reference to an object somewhere on the heap. So, you know, oh, I literally just say that there. Primitive types, the data is stored there. If it's an object, the object is stored elsewhere, but a reference to it is stored in the call frame. And memory addresses of where the program returns when it's done. This is the idea that, like, when a method finishes, it's got to return to the calling method. For us, when we're dealing with high-level programming languages like Python and Java, it's like, well, which one? Well, the one that called it. It's obvious, right? We know that. But the computer needs to know. So you need to tell it, like, return to this method. And kind of, so it can go back to there. Okay, so this is basically where the calling method's call frame can be found in memory. So when running a method, when the running method finishes, it's popped from the stack and the memory that is used is automatically deallocated by the system. Now, the memory management of the stack and the memory management of the heap is a little bit different. The stack is a little bit more like automatic, where the heap, that's where, like, the garbage collector has to come and check if, is this reference anymore? If not, we can get rid of it, that type of thing. So consider, for example, I have this code right here. It's a stupid little program. It's just for demonstration purposes. We have some main. You'll see main, by the way, is a method. It's a static method. It's a method, okay? We have function 1, function 2, and function 3 and function 4. Main calls function 1 calls function 2 calls function 4 finishes, function 2 finishes. We carry on, calls function 3 finishes, we carry on, we finish function 1, we return here, we finish function 1, we finish main. Like, there's like a growing and shrinking of the stack. I've got stack, we push main, function 1 calls function 2, which calls function 4, which finishes, returns, calls 3, returns, main's done, we're done. When the stack is empty, the program's done, or at least the program is not running. So this would be a little animation following the order that that code would run. Is that clear? Cool. That's the idea. Now, this right here is a very important feature of computational systems. Very important to do. It makes programming a lot easier. Heap, very broadly speaking, though, so we talked about the stack. Very broadly speaking, the heap can be broken into two spots: the static spot and the instance space. The static space, that's where, like, the instructions, the code, your classes, your interfaces, all the code is. And then the instance space, that's where all like the information is stored. Like when you create an object, it's put into that chunk of RAM. Reference variables will exist like maybe in the stack, but they will reference an object in RAM. Also, objects might contain reference variables that reference other objects in the heap as well. Instance space, it stores the objects created at runtime, the object type. It knows the object type, the values associated with the object. It includes primitive types and reference variables to other objects. When an object is created, it's put into the instance part of the heap. That's the idea, okay? So we have a stack, we have a heap, and heap has just like where the instructions are, and we're like the data that we're dynamically and whatnot allocating. Objects mostly, stuff that we reference. So we have garbage collection then. We've already talked about this a little bit. When a method finishes running, a call frame from the call stack is not needed anymore, so the memory is deallocated. Okay, that's just like kind of like done automatically by Java. It just keeps track of, like the information on the stack can be overwritten. It doesn't matter anymore. But when an object in the instance space is not needed anymore, garbage collection comes into play. This is where we have to go like, okay, here's an object that exists in RAM. I have a finite amount of RAM. So I might, if this object is in RAM and is not needed anymore, we can reuse it. So it's not wasting space. Clear? So in some programming languages, you need to be explicitly clear about if you allocate RAM, you need to explicitly deallocate RAM. But in a lot of modern languages, this is done for us automatically, like Java. So Java will determine if an object is not reachable anymore, meaning there's no reference to it that I can ultimately get to this thing anymore, it's as good as gone. And if that happens, Java can say, well, we will like assign that chunk of RAM. It doesn't go through and like clear it out, but it'll assign it all to like, okay, this is rewritable. So if you need it, you can overwrite whatever's in there. But as far as I'm concerned, it's just garbage. Yeah.
Is there ever a scenario where it would be necessary to rewrite the allocated like RAM as null?
If you are really concerned about the data, but even like when you delete things on your computer, it's like when you reformat. You ever reformat your computer? There's like sometimes when you, so if you don't know, reformatting your computer is like, I want to like fresh install, pretend everything I have on here isn't there anymore, right? But of course there is stuff there. So what you can do is you can be like, okay, computer, everything that you've allocated, because your computer goes, okay, I know where I've stored all of these very important pieces of information, right? All the video games are stored here, my music, video, whatever, it's all there, right? When you reformat it, what you can say is like, okay, pretend that all doesn't exist anymore, just, it's garbage. Whenever you turn on a computer, there's a bunch of transistors, right? And the transistors have low voltages and high voltages that are decoded to zeros and ones that we decode to have meaning, right? But whenever you turn on a computer, there's always just garbage in there whenever you start. So as far as the computer is concerned, the zeros and ones in there, the low voltages and high voltage, they might have been relevant information, or it may have been garbage. Either way, I don't care. I know I can overwrite it. It doesn't matter anymore. Or when you do a reformat, you could do like a hard reformat where you like go through and be like, wipe. Go and get rid of this stuff. And that could be important for security purposes, right? Yeah.
Yeah, so you don't end up with a hard drive with FBI information.
Exactly, right?
It happens.
Oops, yeah. So yeah. So if an object is not reachable, it can't be used. And when an object is not reachable, there is no accessible reference to it anymore. So like think of this link structure, right? If I lost reference to the, and think about it, right? So let's say I have head in my main, which is on the stack. So it's a reference variable on the stack. I have a reference variable, whatever. But I suddenly make this, like I get rid of this reference so it references something else. This is an object on the heap. Now, if we go back here, we might be like, well, something references this, so it's fine. Well, hold on. There's going to be like a cascading effect. If nothing references this, which means I can't get to this anymore, which means I can't get to this anymore, which means I can't get to this anymore, and so on and so on and so on. So losing reference isn't about like, well, a reference exists to it. Yeah, but can I still ultimately get to that thing? A reference might exist to it, but is that reference also as good as gone? Yeah? Yeah, yeah. This is just showing that. Now Stack Overflow. think we kind of talked about this, right? What happens if I call this function?
Get a fork bomb.
Not quite.
Oh, no.
We have this thing called the system stack, right? It takes up space. It takes up stack space, right? We call a function that calls a function that calls the same function that calls the same function that calls the same function. And we'll just keep putting call frames on the call stack. None of these functions will ever return. There's no bottom, right? It's like looking into infinity. It just, this goes on. There's no bottom, meaning that stack grows and grows and grows and grows and grows and grows and grows in a finite space. We only have so much RAM. So do you think Java's going to be happy or unhappy with something like this? It's going to be thrilled. Yeah, it's going to be thrilled. It's exceptionally thrilled. That's a good word. So no, that's just that's a Stack Overflow. All right, let's go to just something with a main. Does anything in here look like it might have a main? Let's just go here. Let's get rid of all this. And let's just call, oops. When I hit run, what's going to happen? Well, let's find out. Yeah. Is it? Is it, so it's thinking, why is it? It's now, okay, now it's compiling. Okay. All right, it's a very sophisticated problem. Oh, yeah.
It's like, it's stopped.
So, we can. No, we can see. Oh my. We could see it did it. It was doing its thing. You call the function print out we, and then you do it again. And it did. It did a bunch. Quite a bit, actually. Until finally it was like, no. Character buffer, oh, look at this, Stack Overflow. And this is a Stack Overflow. This is where the name comes. There's a stack. There's a finite amount of room. We ran out of room. It overflowed. And it tells us where, and it gives us the stack trace, which is like, remember how I was showing you that stack grows and whatnot? And if you have an exception that came here, it would tell you, okay, an exception came from this function that was called by this function that was called by this function that was called by main, right? That's the stack trace. Now here, well, we got pretty deep in the stack. The function called the function called the function called the function. A lot, right? Like, definitely a lot of times. And it's saying, well, from this function that called that, the same function which called the same function, and so on. We can change this slightly to be like n. And then let's say n plus 1, int n. And let's start with 0, right? So now if we run it, it'll do something a little different. It'll start with 0, and, well, there we go. Whoa. Oof. Well, it compiled. It was happy. Well, we'll find out.
It depends on how much RAM is allocated.
That definitely is going to be true. Well, it looks like it allowed us to call it, oh, come on, 13,855 times. We called it that many times until Java was like, no good. So, yeah, interesting. And if it's unclear why it did what it did, look at the code. if what I just showed you, like why did it do that? What does the code say? When in doubt, what does the code say? That's usually it. Remember, computer scientists are too stupid for there to be any tricks to this. Think about it, right? I call the function, uh-oh, I give it 0. What do I print out? Tell me. 0. And then I call uh-oh, but I give it 0 plus 1. So I call this function again. I start it over, but this time n is what?
1.
And what do I print out?
1.
And then what do I call it again with?
2.
So what is n?
2.
What do I print out?
2.
And then what? And so on. It goes on and on and on and on and on. Now you might look at this and be like, that's like a loop, right? You're doing the same thing over and over, and that looks like a heck of a lot like a loop. Yeah, absolutely. Wait, what's going on here? Yeah, what if I do like, yeah, that's interesting. What if we do like, if n is less than 1,000, oh no, this is not Python. There.
Yeah, wonderful. That won't explode. Now we won't explode.
There we go. It's happy. Right? Makes perfect sense. Why? Well, we get to a bottom. You know how I said before it's like looking into infinity? Now, no, it's not. There's an end. Only call it again. If n is 1,000, it goes, don't do this. I'm done. Return to the calling function. So it returns to this line, and it goes, oh, I'm done. And then returns to the calling function, which would be this line, and then goes like, well, I'm done. And so we go all the way down. That call stack grows and grows and grows and grows and grows until there's like 1,000 things on it. And then it returns until we get to the end. What would happen if I did this?
This feels kind of like Haskell, which could be wrong, but
It definitely does. It definitely does. You think it would start at 1? Well, let's find out.
oh no, it would just print in reverse.
In reverse order. Why? What does the code say? I will never get to a print until, so when n is 0, I go into there. I start over. N is 1. There. Eventually, n is 999. I go into there. Okay. N is 1,000. I skip. I go down here. I print out n, 1,000. I return to the calling function, which is here. N is now what it was before, which was 99. Because remember, the value of n is stored in its call frame. Each call frame, when I call like the 999, the value in there of n is 999. When I call it again with 1,000, I push another call frame on, but that call frame's n is 1,000. So each call frame knows it's like instances n.
So call frame is like a namespace for the stack, kind of?
Effective. Well, for like a thing on the stack, yeah. And so yeah, reprints it in reverse order. So we go all the way till we get to 1,000. Then we print and return, print, return, and so on and so on. So what happens there? Trouble. But we can contain that trouble. So recursion. Useful. Recursion is this idea of solving a problem by like, so recursion is like when something is defined in terms of itself. And sometimes you could take this idea to like solve a big problem by actually solving the exact same problem, but a smaller version of the exact same problem. I'm going to highlight this by saying how many people are in this room right now, okay? So, not very many. That's why we could do the whole room. So how can I do it? Well, I could stand here and go like 1, 2, 3, but that's boring. No, I'm too lazy for that. Here's what I'm going to do. I'm going to say, well, here's what I'm going to do. If I knew how many people were in this room, excluding him, then I know that the total number of people in the room is the total number of the people in the room excluding him plus him. Do you agree with that? So I know that it's like 1 plus how many other people are in the room. So that's the question I'm going to ask you, right? So the question you have to say is, how many more, assume we have a line that goes like this. Okay, so you're the last person. Okay, you're going to be the first person. So for you to know how many people are in this room, you need to know how many people are like behind you in line plus yourself. So you know that if I asked you how many people are here, you just have to know, well, it's everyone behind me plus 1. Now he can't tell me that because that's ridiculous. How many people are here? Oh, however many other people plus me. Well, that's stupid. But what he can do is say, well, why don't you ask him? So ask him how many people there are, right? So ask him, how many people are there? And you go like, well, I don't know. But I know it's however many people behind me plus 1. So you ask him. And you know it's going to be however many people are over here plus you. And then you just got to tell him that. So ask him how many people are there. And then ask him. 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 And now he is in a bit of an interesting situation. He looks behind himself and goes, oh, well, it's how many people are behind me, which is 0. You know the answer to the question. Meaning, how many people are there plus everyone behind you? 0, including you. What's 0 plus 1? 1. Right? So he knows how many people there are. So now because you know how many people there are, you can tell him.
The people that are here are B plus however many people are in front of me.
Which is what?
Which is 1.
Which tells you how many people there are.
There's 2.
Which tells you
There's 3. 4. There's 5. There's 6. There's 7. 8. There's 9. There's 11. There's 12.
there's 12. Because he finally got, obviously we asked the, I don't count, I'm special.
But you asked him first.
Yeah, but I was the calling method, so I don't really care. So the point is, we all asked each other the exact same question. It was just like a smaller version of it. But the exact same question was asked. Okay? And at the end of the day, we started by asking him how many people there are. And you said, it's however many behind me plus 1. And you didn't have the answer to everyone behind you, but you asked somebody else who, through recursion, answered it. But you don't care. You don't give a shit. You don't care how he got it. All you know is that you got it. So as soon as he told you 11, you were like, it's 12. It's however many people behind me. I just need an answer to that question. How do I get it? I'm not worried about it. Someone else will tell me. They get back to you, and then you can answer. And this idea is exactly what we were just doing in that loop effectively, right? Or in that counting recursion. But anyways.
It's a bit like a game of telephone.
It is. A much more accurate version, right? So in this example, like just by looking at the first person, it's exactly, like how many people are in this line? Well, it's 1 plus however many people behind him. And you're left going like, that feels kind of annoying, but I go like, nah, that's cool. Trust me, we're fine. Because again, it's 1 plus however, and so on. So iterative definition versus recursive definitions. This might sound like I'm coming up with contrived examples, but I'm really not. Like this is the difference, right? Like I could go and define a group of people. Everyone in here knows what a group of people is, right? What is a group of people? Well, I could go and be like, well, a group of people is going to be like 2 people or 3 people or 4 people or 5 people or 6 people or 7, and we can go on forever, right? Like this is, it's an infinite thing, right? As long as you have more than one person. But like that's an iterative definition, like, exhaust the things. But we can use the idea of a group of people to define a group of people, which is weird. But we're going to start defining things in terms of themselves, which sounds like we're cheating, but I think you'll all actually go with me on this pretty well. When defining something recursively, you define it in terms of itself. Define something in terms of itself. So a group of people is either 2 people or a group of people plus 1 more person. So if I ask you the question, is 2 people a group of people? You look at the definition of a group of people, and what do you tell me? Is 2 people a group of people?
Yes.
Why? Because it says right there, by definition it is. There's no ifs, ands, or buts. It's right there. And I say now, how many, is 4 people a group of people? And then you look at this and you go like, well, I don't know. Maybe. Yes. Well, like I know that, like in order to know if 4 people is a group of people, pause. I know, as humans, we're all like, yeah, I know. But let's think about the steps that this means logically. Now, when I say logically, I don't mean like, oh, we're smart. I mean like really like the mathematical like steps that one would take to draw these conclusions. So in order to know if 4 people is a group of people, it needs to be known if 3 people are a group of people. Because if 3 people are a group of people, and I'm one more person, then then that group is a group of people, right? Because a group plus 1 more. So if 3 is a group, and I have 4, 4 is a group. So I need to know, is 3 a group? But I don't know. 3 is a group if 2 is a group. Because if 2 is a group, plus 1 more, 3, then 3 is a group. And if 3 is a group, 4 is a group. So we need to know if 2 is. We look at 2 and we go like, oh yeah, it is. So if 2 is a group of people, that means 3, because 2 plus 1 is 3. So by this part of the definition, 2 is a group by this part, 3 is a group by this part, 4 is a group by this part. In fact, 5 would be a group by that part, and so on and so on and so on. Yeah, so in the above recursive example, you'll notice there's like 2 parts of this definition. This is a recursive definition. We've defined it in terms of itself, but it includes 2 important parts. Not all recursively defined things necessarily need the 2 parts. We saw some examples of some recursively defined things that didn't have 2 parts. What we just did, where it ran forever. We have what we call a base case, like something that is just a matter of fact. And then we have the recursive case, the part that really is defined in terms of itself. If I write a recursive thing, chances are we want both of these things, the base case and recursive thing. You could be missing this, you could, and you might make it work for yourself or not. It's hard to say. Excluding this, we saw could cause problems. That's like that uh-oh, right? There was no base case. There was no stop. There was no, right? That we went on forever. But what's interesting here, though, is the fact that we had a Stack Overflow, that had nothing to do with the rules of computation as defined by Java and within our universe. And I don't mean that as a grandiose, like, yo, dude, within our universe. I mean, like, really, in terms of how this works and how it's defined and the steps we follow, this is all true within our universe. That Stack Overflow didn't happen because we broke the universe. It broke because of a constraint, a physical constraint of Java on our computers. If we were to somehow implement this idea physically and just say, go, nothing would stop it from happening. Right? Which is kind of neat. Like that process would run forever, which is kind of neat. Anyways, a lot of things in real life are recursive processes, by the way. Anyways. All right, warning. Although there is no hard rule saying the base case is needed, and there are examples of situations where it would not be, for example, uh-oh. For the purposes of our course, we're like almost always going to have base cases. You can have a recursive call have multiple recursive calls too, right? You might have 1 base case and 2 recursive calls. It's kind of neat. And we'll see some examples of that shortly. Now a list. A list is a data, like look, think of a list. You can think of a linear bag, whatever, right? But think of a list like we were used to in Python. We could define a list recursively really easily. A list is either an empty list or a head followed by a tail where a tail is a list. That's what we will say. We have an empty list is a list, or something where like we have a head of a list followed by a tail which is also defined as a list. So what I mean is consider this list. A, B, C, D, and E. Is this a list? Well, I can get a head out of this list, A. And there is a tail, which the question is this a list? If this is a list, then this is a list, because I have a head followed by a tail, and if the tail is a list, then the whole thing is a list, right? So we can keep doing this over and over and over again. Okay, so if I do it again on that sublist, which was this, and take the B out, okay, B plus its sublist, and then C plus its sublist, is that a list? Is that a list? Is that a list? It's an empty list. Why is that a list? Because we said so right there. So if that's a list, then we know this is 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 a list. Recursively define the list. This might seem silly, but this is a very powerful way of thinking. Repeating patterns. So in the counting example, it might feel like cheating by saying like 1 plus however many are after the front, right? Like in the people in the line example, or what we just did here. But we saw that it worked, right? Like the however many are after. Like when I asked you, like how many people are in here? It's, well, you plus however many other people there are. It feels like the however many other people there are is like skipping a step, right? Like, want to hear a really cool sorting algorithm? If I have numbers that are unsorted, this is a really cool sorting algorithm. And this is how it works. If I have a group of numbers over here that are unsorted, and a group of numbers over here that are, let me fix it. A group of numbers over here that are unsorted, and I'm a number. Let's say I'm the number like 100. So I have numbers between 0 and 99. They don't have to be 0 through 9. There could be duplicates. There might be 4 numbers here, 500 numbers here. I don't care. But they're less than me, and they're not sorted. And I have numbers over here that are bigger than me, and they're not sorted. You want to know how to get a sorted collection of everything? You sort that, you append me to the end, and then you sort that and you put it there, and I'm a big sorted list. And you're left going like, well, how do I sort it? Oh, just sort it. And you're left, what? Turns out that description, it'll work perfectly. And we will see this as we carry on in the course. But that's an example of the like, well, hold on. We can sort it by just sorting it? Yeah, you'll see. You'll see, you'll see, you'll see. I am missing one key element. You want to know a key element here?
Sure.
If that list over here, if that collection over here has one thing in it, is it sorted? Is it out of order?
No, that's only one thing.
Yeah. And what if it's empty? Is it sorted, or is anything out of order?
No.
That's the other half of the magic to this idea. We'll get there. We'll get there. I don't want to spoil the fun. All right. So with the list example, it was observed that repeatedly applying the same rule over and over and over to smaller versions of the same data, we saw that like we hit an end, right? Like the empty list, the base case. This pattern arises a lot in recursion where, solve the same version of the problem, but a smaller one, 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 until finally you get to like an end where something happens, where we kind of trigger that base case or something. Yeah. Going up and going down. So here's another key concept to follow. Let's think of the set of natural numbers. We can define these things recursively. Now, defining, with this recursive definition, we have a couple of ways we can kind of think about it. They are ultimately the exact same way, but you kind of can think about it from two different directions, right? I can start with the base case of 0. Okay, is 0 a natural number? Let's say it's a natural number. Okay? I can start with the base case, and I can then say, I can repeatedly apply the recursive case over and over and over and over again to generate all natural numbers, right? 0 is a natural number. A natural number plus 1 is a natural number, meaning 0 plus 1 is a natural number. It's 1. 1 plus 1 is a natural number. 2 plus 1 is a natural. So I can start from the base case and go like up, right? Yeah.
Yeah.
It is.
They would be whole numbers.
They'd be whole numbers?
Yeah.
I'm saying it is here, so tough.
Yeah.
As defined by me. Is 0 a natural number? Isn't this one where it's like,
It's kind of ambiguous. It's usually not.
The
but
natural numbers
some
are
people
0.
seem to say it is. Well, no, if you click on it, don't listen to Google. Listen.
no, I'm listening to Google.
It's Wikipedia.
It's Wikipedia. This is not a generate.
If you read the
Yeah, but then some weirdos say it's not. So,
It's some weirdness. I think it's most weirdos.
yeah, okay. I think I even, maybe I do say in there where I say non-negative integers, but some author note, whatever convention, sometimes the whole numbers are the natural numbers as well as 0 in the cases.
Wait, so it's the natural numbers are 0, 1, 2, 3, and so on, possibly excluding 0.
According to some weirdos.
Sheesh.
Sheesh.
Natural is 1.
So, as defined by me and Wikipedia, and excluding those weirdos, 0, pardon? Britannica? But who trusts those weirdos, too? Come on. So, natural numbers starting at 0, we can generate them all by repeatedly applying the recursive definition, right? We start at the base case and we kind of like go up. But we could also start at like 4, where we're not starting at the base case, but we ask the question, is 4 a natural number? In order to know what 4 is, we need to know if 3 is 2, is 1, is 0. Ah, it is. Now we go back up to 1 to answer. So we can like start at the base case and go up, or work our way down towards the base case. There's like a directionality here. Ultimately, it's the same thing, don't get me wrong, but you know, you can kind of think of it depending on how you're approaching these problems. All right, so is 4? Well, is 3 plus 1? Is 2 plus 1 plus 1? Is 1 plus 1 plus 1 plus 1? Is 0 plus 1 plus 1 plus 1 plus 1? Yes. Which means 0 plus 1 is, which means 1 plus 1 is, which means 2 plus 1 is, which means 3 plus 1 is, therefore 4 is. Yeah. Cool. Cool. We've seen this before. N factorial, right? Yeah, this is recursively defined. We like to define factorial recursively. Now, I will tell you something. Spoiler. You will notice that, hey, it's like a loop, right? Repeating the same code over. It's just like a loop. You're absolutely right. Anything you do with recursion, you can do with a loop. Anything you do with a loop, you can do with recursion. It's the same. Sometimes, so whenever you're writing code to solve a problem where like looping and iteration is required, you might be put in a position where you're like, should I do it recursively or iteratively? Should I use a for loop or should I use recursion, right? You have a decision to make. You can do anything. I see, give me a sec. I can do one or the other. It's a decision to make, right? Sometimes the code for recursion is just so much nicer. We want high quality, good looking code. So a recursive definition might just be so natural that it's really good. And sometimes it's not. So, you know, it's just another design consideration. Yeah?
I was going to say, does that mean that recursive programming is of the order n factorial?
No, not at all. No. Well, it could be. It depends on the problem. The style of programming, it would be the algorithm that if you wrote a recursive algorithm, but it wouldn't be because by virtue of being recursive, it would be by virtue of the algorithm that you implemented. Like I can write a for loop to count to 10, or I can do a recursive thing to count to 10. It's still going to be linear, right? How many times does this chunk of code run, right? That's always the question you have to ask. When it's a loop, it's easy to look at. When it's recursion, it might not be as easy, but it's still pretty easy. But you'll see. We're going to talk about that shortly. So factorial. Factorial of a non-negative integer is the product of all non-negative integers between n and 1, right? So it also includes 0, but this is addressed below. Yeah, you can get 0 factorial, but 0 factorial is defined as 1. We'll talk about that in a second. So n factorial is n times n minus 1 factorial times n minus 2 factorial times yada, 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 3 times 2 times 1. Okay? That's factorial. And you might look at this and be like, that looks like the same thing over and over, which it absolutely is. And here is the recursive definition of factorial. This is often how you see it defined. N factorial, if it's 1, or if n is 0, it's 1. If n is greater than 0, it's n times n minus 1 factorial, right? That's the recursive thing, right? So if I say, what's 3 factorial? Well, you go like, well, 3 is greater than 0, so it's 3 times 2 factorial. What's 2 factorial? It's 2 times 1 factorial. What's 1 factorial? It's 1 times 0 factorial, 1, 1, 2, 4, yeah, and so on. So, yeah. So one thing you'll kind of notice, this is like a neat little quirk. Don't ask me more than what I have here. 0 factorial is 1, actually, which you might say is like, that's weird. Shouldn't it be like 0? Well, no. First, it is 1 by definition. Whenever you define something like this, and you're like, why is it 1? And I say something like that, and I say, because it is. And you're like, why? And I say, because I said so, right? That's really it. I defined it as such. So first of all, we can do that. But also, 1 is the multiplicative identity. 0 is the additive identity. Basically what I mean is if I say 5 plus 0, you leave the thing alone, right? It's like an identity value. It makes no change when you apply an operator. For multiplication, the identity is not 0, it's 1. 5 times 0 destroys it. That's an annihilator. 5 times 1 it leaves it alone. So that's also a big why. And also, it aligns with the gamma function, which is a generalization for real numbers. So anyways, we'll stop here. Pick up with factorial on Tuesday.